Hello everyone, my name is Nikolay Karpov. I work as a data scientist of speech technologies at Sber devices department. I'm going to tell you about how we are improving automatic speech recognition models using transfer learning between languages. My agenda is following. First, I will start from motivation, a comparison of pre-trained QuartzNet and ContextNet from scratch. Second, I will show how transfer learning works for different languages from English to Russian. Third, I will talk about experiments in transfer learning from QuartzNet to ContextNet-like architecture. Fourth, I will present transfer learning from big to small QuartzNet. Okay. Let me start from products with speech recognition in Sber. Sber is a digital ecosystem with Sberbank as a center of the ecosystem. It is the biggest bank in Russia and Eastern Europe. Sber ecosystem has more than 100 million customers. Sber devices is a part of it, and we make smart devices, develop computer vision and biometrics technologies. Of course, we develop speech recognition and synthesis technologies. They are used for many products. Some of them you can see on the slide. For instance, speech recognition for call center, duplex technology, smart home, and so on. All these products need a good speech recognition system. Our current speech recognition created using convolutional neural network called QuartzNet. And last year, authors from Google published a paper about ContextNet called Improving Convolutional Neural Networks for Automatic Speech Recognition with Global Context. In the paper, authors say that the lack of global context is the main cause of the gap between the convolutional neural networks model and the transformer-based models. To bridge this gap, the authors propose the squeeze and excitation layer. Also, they use LSTM as a final layer, also called a decoder. Just a few words to remind you what is a squeeze and excitation model. If we have a tensor in the model like a green on the slide, where the horizontal axis is time, it consists of a sequence of vectors for each time frame. Then, as E layer is additional manipulation on the tensor, it averages vectors over time, then decrease the dimensionality of the vector and increase it back, propagate the obtained vector over time and multiply it with each of vectors in the original tensor element wise. The resulting tensor has the same dimensionality. Our experiments show that ContextNet from scratch cannot outperform our pre-trained QuartzNet model. This was a motivation to do further experiments. Next, I'm going to explain an algorithm how we perform transfer learning from the English language to the Russian one. Basically, it is a little bit similar to how authors from NVIDIA propose it in their paper called Cross-Language Transfer Learning, Continuous Learning and Domain Adaptation to End-to-End Automatic Speech Recognition. In this paper, they analyze 3 use cases for transfer learning: different English accents, different languages, German, Spanish and Russian, and application-specific domain. Our transfer learning algorithm from English to Russian acoustic model is following. We take an encoder from QuartzNet 15x5 model as is, which pre-trained on 3,300 hours of public data in English. Our target domain has a different alphabet, so we map characters from old decoder to the new one. We randomly initialize weights for new characters in decoder, then train the resulting network on a target dataset with the same size and starting with the same learning rate that was used to pre-train the model from scratch. All our experiments were performed 100,000 steps on 16 GPU. Each step accumulates gradients of 10 batches with 88 samples. This table shows a mapping of weights from Cyrillic letters to Latin ones. We map pairs of letters that have similar pronunciations. Some of letters without pair initialize randomly. Our results we evaluate using word error rate on two test sets, simple and difficult one. Small values of word error rate mean a better result. Experiment with transfer learning outperforms by 10 and 15% relatively a baseline with random initialization. It is a great improvement just to start from a pre-trained checkpoint. Let's go to the section about transfer learning from QuartzNet to ContextNet-like architecture. This slide helps us to compare the structure of ContextNet versus QuartzNet. Both of them are convolutional and looks like a sequence of layers with increasing number of channels. A difference is that ContextNet has an additional SE layer for each convolutional block. Also, ContextNet has a LSTM decoder versus fully connected decoder in the QuartzNet. Okay, we have QuartzNet pre-trained on English language, and we want to transfer its weights to ContextNet. We modify QuartzNet architecture to add squeeze and excitation layer and LSTM decoder to be it more like ContextNet. To analyze how modification affect results, we compare QuartzNet pre-trained on English with SE and LSTM layers and QuartzNet randomly initialized with again SE and LSTM. We call such a network a ContextNet-like architecture. This slide shows the graphics of word error rate of ContextNet-like architecture. We can see that the pre-trained version is better than from random, but improvement is half and 5%. That is much less than what we had for pure QuartzNet, like 10 and 15%. Let us go deeper and analyze how different parts of ContextNet-like architecture affect the performance. We take several models like QuartzNet with random initialization, QuartzNet with SE and LSTM with random initialization, and so on. Like QuartzNet pre-trained on English plus different parts. All experiments were performed 100,000 steps on 16 GPU again, and each step accumulates 10 batches with 88 samples. The first figure shows word error rate of model on the simple set. Here again, small value of where means a better result. We take QuartzNet with random initialization as a baseline, and values demonstrate improvement relative to baseline. The best score shows pre-trained QuartzNet, and we can conclude from this slide that the less random we have during initialization, the better the final result we have. The second figure shows the wear of models on the difficult set. The best score here on the pre-trained QuartzNet with LSTM. It is 18% better relative to QuartzNet from scratch. And a takeaway from this slide that pre-trained weights are more important than new improved architecture. The final topic is transfer learning from big to small QuartzNet. We train a small QuartzNet 5x5 to use it embedded on the device. In order to do it, we take pre-trained weights from big QuartzNet 15x5 and transfer them to QuartzNet 5x5 layers of the same size. The structure of two networks is shown on the slide. QuartzNet 15x5 has 19 layers and the 5x5 only 9. We map first layer of QuartzNet 15x5 to first layer 5x5, second to second one, fifth to third, and so on. The results are following. On the 10,000 steps, a performance of model started from English and Russian pre-trained weights become much better than trained from scratch. Word error rate values is almost 2 times less than baseline. It means that it is not so important which language to use as a started checkpoint. If we train longer, then the graphics will be changed. This experiment takes 5 times longer, 50,000 steps. The difference becomes lower, but still model started from the Russian language was almost 10% better than the baseline, and pre-trained on English shows 5% improvement. We can conclude from this slide that transfer learning can be successfully applied to different architectures. Let's have a look at the same results from another perspective. If we use transfer learning, you can achieve quite a good results by training 5 times faster and cheaper than without it. Okay, let me summarize my talk. We show how pre-trained weights affect the final word error rate of QuartzNet. We demonstrate scores for ContextNet-like architecture, means QuartzNet with SE module with LSTM decoder, and we show how small QuartzNet benefits from pre-trained big one. Conclusion. We find that final performance is always better than starting with pre-trained model versus training from scratch. transfer learning can be successfully applied to different architectures. Pre-trained weights are more important than new, improved architecture. And which language to use to pre-train a model is not so important. Thank you for watching.